We'll see how that. So spam comments are no big deal, but still. All right. So here we go. I will answer whatever questions on the homework you have. Yes, sir. I did. I'm sorry. I did record it, but I did not post it yet. I'll try. 4.24. So I don't know if I can do that question or not. I have to, well, I'm sure I can do it, but let's see. What number is it? 1 through whatever. Oh, I logged out of stupid mastering. So yes, I can do it, but I will have to log back into mastering. So, while we wait for that, maybe I'll get the lights. Oh, mastering. You doth heartless bitch. Takes so long. I don't know why it takes so long for my computer to log into stupid mastering. Just which one is it? I probably have it memorized by now. What's it about? Is it the person pushing on the box? Okay, that's like number 1, right? Okay. All right, person pushing on the box. Number 1. So I'm not going to do your version of the question. I'm going to do everybody's version of the question. And what I mean by that is I'm going to solve the every problem. I'm not going to put your numbers in. And that's because I want you guys to get accustomed to seeing these as expressions as opposed to having them with specific numbers where you tend to start filling in the values sooner than necessary. So this is our problem, isn't it? Something like this. They're pushing at some angle, 30 degrees to the horizontal. And due to that, the box is sliding at a constant velocity. That's probably the most important thing that's brought up, is that the box is sliding at a constant velocity. So the net force is 0. Once I've established that, the box has mass m, and there's a coefficient of kinetic friction between the ground and the box. This problem, I would argue, is probably beneath the level of the test. There's nothing particularly interesting here. And I don't believe it asks enough to be interesting, except that it does want you to find the size of the pushing force, which does make it a little interesting, I guess. And the reason why is because the pushing force determines the size of the frictional force. If you aren't wrapping your brain around this, it's about time that you did. And here's where, you guys taking notes might matter. We're pushing downwards on the box. This is going to increase the size of the normal force, and friction is proportional to the normal force. So if I push down on something, I make it harder to move that something, because while I'm pushing down on it, I'm also making the frictional force bigger. You should be able to explain why pushing slightly downwards on something makes it more difficult to move. And when you do, you should be able to explain that entire chain. That friction is proportional to normal force. Pushing down increases the normal force. Therefore, it increases the frictional force. But I'm boring people in the classroom because they're stretching and yawning. So let's move forwards. I have an applied force like that. Weight, probably like this. I have no idea the proportionality here, but I would imagine that my frictional force would have to be at least that big if I want to make them in the correct proportion. Meaning, I'm going to be checking this time on your test that you have made a reasonable attempt to draw the size of the arrows correctly on your free body diagram, which in this case means that I have a frictional force that appears to balance the forward portion of the applied force. So I'm looking at the horizontal part of that F that I just drew and drawing my friction to be about the same size. Any questions out there? All right, we'll see. Because there's also, I have this acting downwards and this acting downwards. So I need a normal force that appears to balance that. So I'm going to draw my normal force big enough so that it looks like it encompasses the size of the weight and the downward part of this force. If yours doesn't, it's going to be wrong. So on your next test, it's not just about the directions of the arrows. All right. We've done these a lot, so I don't feel too compelled to spend lots of time going over the individual parts of this. This is going to be my positive X direction. This is going to be my positive Y direction. I have drawn a free body diagram. I've indicated all the forces acting on the object. I have one force that appears to be off axis. So I will break that force into components by wrapping a triangle around the angle, with the angle being here. I will perform trig and show that the horizontal part is based on the cosine and the vertical part is based on the sine. So I've performed my trig. Any questions about this? I will apply net force in the X direction equal to 0 and net force in the Y direction equal to 0. This will complete applying Newton's laws. So F cosine theta minus friction equals 0. Normal minus mg minus F sine theta equals 0. Taking notes, Adam? I hope so. So that's it. That's all that Newton's laws can do. They've brought me to this point. I don't know that I can solve the problem with this alone, but this is as far as Newton's laws can take me. Now, they want me to solve for F, and it appears in two places. It is unlikely that I'm allowed to have friction in my answer or normal force in my answer. And that's not uncommon. What they want is for me to utilize the coefficient of friction. The coefficient is the percentage of friction. They are asking me to combine these two things to make the connection that friction equals mu times normal force and to pass the normal force through. You will need to do substitution. It's your only option here. So it's not a big deal, but if you're not prepared to do that, remember, it is the percentage of the normal force that makes up the frictional force. So I'm going to solve for normal force first, which is going to be F cos theta plus mg. I'm going to multiply both sides by mu. Why? Because that makes it the frictional force now. Once I've done that, I can substitute in for friction. So F cos theta minus mu F sine theta. I wrote cos and I meant sine. Sorry, I made a boo-boo. 1 point off of my test. F sine theta minus mu mg equals 0. You need F by itself. So you need to kick this guy over to the other side of the equation. Done. And then I need to collect F. So I'm going to separate it from its friends. And then I'm going to isolate it by itself. Making it stay at home for 2 weeks until it's all better. That's it. There's probably more to this problem, but once you have the size of this force, you've got the rest of the problem done. So, you're going to plug in all your numbers, and then you'll go through and you'll be able to find the normal force if you need it. It's right here. then the frictional force if you need it, because it's right there. And those are the two things that it asks for part B and part C. Yes, ma'am. Say that again. I couldn't hear you. I'm sorry. Anytime you get to a point where all you have is a force, an equation with friction in it, and an equation with normal force in it, you're very likely going to have to combine those using F equals mu times the normal force. That's usually right where it is. So when you get to a point where you have an X and a Y equation that are, that each have this one unknown variable in it, that's what you do. You're going to combine the two of them. That's really what all that frictional equation does, is it makes you combine the X direction and the Y direction together. Does that make sense? All right. All right, is that enough of number one? All right, next question.
Problem 4, hold on. Problem 4.53. Sorry if I interrupted anyone.
Problem 4.53. No idea what that one is. So, all right, that was number 5 in the old homework. Problem number 5. Says 2 blocks, mass M1, M2 are connected to each other on an Atwood machine. The blocks are connected by a string going over a light pulley with no friction in the bearings. A person holds one of the blocks with their hand. When the system is released, the heavier block moves down with an acceleration of 2.1 meters per second squared, and the lighter object moves up with an acceleration of the same magnitude. Suppose that the lighter block has a mass of 100 grams. All right. Well, let's do this for every single Atwood machine because they're all the same. So there's my huge pulley, and it is connected through a light, thin, and frictionless bearing, and it connects block 1 with block 2. Yay! So we did this Atwood machine question in class, and all Atwood machine questions end up being the same once you've done one of them. So this will be no different. This has, let's see, M1 and M2. And we don't know which one's lighter, so pick one. Which one do you want to be the lighter block? M1 is the lighter block? Fine. So we think it's going to go this way. Is that fine? I really don't care. It's the same problem, whether you make it go that way or go the other way. But there was some issues yesterday in tutoring that once I decide a direction for the pulley, I am deciding the positive direction for each box. So with your free body diagram, I would expect you to do that. Moreover, although this is not the way the book does it, this is the way I do it. If you don't like this way, use the book's method. But I'm going to draw M2 in such a way that its gravitational force is less than the tension. That has to be purposeful because I want to make sure that I have a picture that represents that the unbalanced force is downwards. On M1, I'm going to draw the tension force to be the same size as the one I drew for M2. It is the same string, and if the pulley has no inertia and there's no friction, then the tension should be the same everywhere in the rope. I should have the same size T on both of them. And lastly, I should draw M1G, the weight of block 1, to be less than the tension since it has to be pulled upwards. All of those things have to be in your picture. If they're not there, it's wrong. You will lose points. Actually, you just won't gain any points. Any questions about why I drew them the way I did? All right. The system is accelerating. This is a Newton's second law problem. So net force equals MA. On the right block, that means M2G minus tension equals M2A. Any question about that? Go ahead. Right. All right. And so for the other block, I have T minus M1G equals M1A. Remember, I'm adding up all the forces, taking into account their direction, and setting them equal to the acceleration. I did it on both sides, just following the instructions. And when I'm done, I have a system of equations that is custom fit for this situation that solves the problem. It might not give you the answer you want, but it will solve the problem. And this is where we are done. We have used Newton's laws. You might have to do more, but we have used Newton's laws. This is as far as Newton's laws will take us. Now, Newton's third law does assure us that this tension and this tension have the same magnitude. That's Newton's third law, that these are a third law pair. They act in opposite directions on both objects, but they're the same size. What you usually have to do next is eliminate the internal force, the Newton's third law pair, and that's this one. And I would encourage you to consider not using substitution. You've been using substitution for years. Maybe it's time to do something else. Because you start using substitution, you start screwing up signs. It happens all the time. I watch you guys do it. So instead, take this guy and write him underneath the other one. T minus M1G equals M1A. Add the two equations together. Meaning add all the things together that are on the right side. That would be M1A plus M2A. Just adding them together. And add all the things together that are on the left side. That's going to be M2G minus T plus T minus M1G. But you should see right away that these cancel a lot. That's what will happen every time. Whether you have 2 objects or 5 objects in a row, the internal forces will all cancel out. And what you'll be left with are the external forces on the system. More than that, you're going to be left with something that you should be looking for in these problems specifically. If you've done this correctly, you should see the sum of all of the moving objects. If you've done it correctly, anything that's accelerating should show up added together, their mass. If you've done it incorrectly, they won't be there. But if you've done it correctly, all of the things you've added together will show up there. And that's how you know you've done it right. The inertia of the system will appear in the problem. Moreover, that's the unbalanced force. The weight of M2 and the weight of M1, they're unbalanced. If they were the same weight, that would be 0 and the system wouldn't accelerate. Anyways, that's the answer. Whatever that is what you want. That's how you get the acceleration. That's how you find the tension. I don't know what the rest of the problem's about, and it doesn't really matter. If you're trying to solve for M1, they gave you the acceleration, so you can figure out M1. If you would like, I will do the algebra to show you how to get M1. Because I know somebody from second period asked about this. I think it was Nathaniel. If you want me to do this to solve this for M1, I will. So M2G minus M1G equals M1A plus M2A. So I get to do algebra for today. So excited. So to solve for M1, M1 has to be on the same side. So M2G minus M2A equals M1A plus M1G. I've got them on the same side. I will collect like terms because it's a joy. And then I will divide everything that's not M1 to the other side of the equation to give me m2g minus m2a over a plus g. Yay. All right, I'm not doing your algebra anymore. Do your own algebra.
Thank you.
Yep.
You didn't.
Next. If there's more to this question, I'll do it, but I don't think there's any more to this question.
No, thank you.
Number 8.
All right. Number 8, is that the skier going down the slope?
Yeah.
All righty. Number 8 is a reasonable problem. It is, I would say, within the boundaries of what you should expect on your test, maybe a little simpler than some of the stuff that's on the test. It is a single body problem involving friction and a ramp. So it's not particularly interesting, but it does have something else that might throw you off. So we have a ramp angled theta, a child on a sled labeled M, and we're told that the ramp is, I don't know, L long. There's more information in the problem. You can look that up. There's a coefficient of kinetic friction between the block and the ramp. Now, there's a bunch of numbers for this, but everybody has different numbers. So let's do everybody's question. This problem asks, what is the velocity of the sled when it makes it to the bottom? Newton's laws can't tell you the velocity of the sled when it makes it to the bottom. And you should know that because I've headed off every single problem by telling you that the only thing that Newton's laws can ever tell you is the size of an individual force and an acceleration. That's all it can tell you. But it can tell you an acceleration. And since we know the initial velocity is 0 and delta x is L, that should clue you in that maybe Newton's laws will give you the acceleration. And then you can use a motion equation to figure out how fast it's going. If it didn't clue you in, then you have been dormant for the last 3 weeks, 4 weeks, 6 weeks. So you have 2 parts to this problem. You're going to use Newton's laws to figure out the acceleration, but then you will use motion equations to figure out the velocity. I will do one of those 2 parts, the part that has to do with force. Should I expect this on the test? Yes. I should expect you to know your motion equations, all 5 of them. Your equation sheet gives you 3 of them. But I should expect you to know all 5 of them. Keep that in mind. So let's do the problem and see if Newton's laws can tell me the acceleration of the system. I'm going to start with the free body diagram for my object, beginning with the weight downwards. Normal force perpendicular to the ramp. And friction, a small force up the ramp. Small because I believe the block is accelerating down the ramp and is getting faster. So I need to make sure that my component of the weight down the ramp is greater than the frictional force. If the box were slowing down, it wouldn't have a final velocity at the bottom of the ramp. Not if it started from rest. It would never have started moving. So I'm assuming it's speeding up. That's the only thing that makes sense. So with that in mind, I can begin the process of evaluating the ramp. I will start by putting in a coordinate system that is aligned with the ramp. This is my positive x direction. This is my negative y direction. I will assign the angle here because that's where it goes. I will wrap a triangle around the angle. And I will do my trig. mg cosine theta, mg sine theta. There, I've drawn a free body diagram. I've applied a coordinate system. I've identified off-axis forces and found their components. I can apply Newton's laws now. And the first one states that the net force in the x direction is equal to ma. I have 2 forces in the x direction. mg sine theta minus friction equals ma. Now, before I have that person show up at tutoring this afternoon, because there is no tutoring on Tuesday afternoon, so I won't see that person. But let's just say that I've gotten a couple of Canvas messages in the last 2 weeks that have said, I have no idea what I'm doing. Then why are you silent right now? Because at any one of these spots, if you didn't know what I was doing, you should be saying something. These problems are all the same. And if you've noticed, I keep repeating myself purposefully for you to hear me say the things like, I have put my free body diagram down. I have put a coordinate system on my free body diagram. I have broken my off-axis forces into components. If these things aren't making sense to you, then you should be stopping me at any one of those steps that doesn't make sense. But have I done anything different in the last 3 weeks? All right, I keep going. Net force in the y direction is equal to 0. Because it's only I purposely made sure that the coordinate system was lined up with the acceleration. I have 2 forces in the y direction, normal force and part of my weight, and they equal 0. That's it. That's all forces can do. Forces can provide me with a set of relationships that I may or may not be able to use to solve my problem. And I will point out I need the acceleration. And right now I am stuck. I can't get the acceleration because I don't know the frictional force. However, they told me that this is the percentage of the normal force that provides friction. So if I find the normal force, I can multiply that by that percentage, and that will give me the frictional force. So that is a plan on how to use what I found with Newton's laws to solve my problem. I'm going to try that plan and see if it works. So solve for the normal force. Multiply both sides by mu. When I do so, that means this is the frictional force. I've multiplied the normal force by the percentage to get the frictional force. Now that I have the frictional force, I can substitute it. So I will get mg sine theta minus mu mg cosine theta equals ma. Now, yeah, that's not particularly pretty, but I will state that I can get rid of all the m's. And that leaves me with the acceleration equals g times sine theta minus mu cosine theta. So you get the work there. I don't know what your angle was. I don't know what your value for mu was, but that's going to provide you with what you need to figure out the acceleration. And then you guys can do motion equation problems. I am not going to do a motion equation problem for you. Any question about that? Because that's just part A. There's part B. What's that? You'll be given everything that you need to solve a problem. So, but I'm not going to say you'll be given mu, especially not if the question asks you to figure out what mu is. So let's talk about what part B of the problem is, because part B does flip the script on this problem a little bit. Because in part B, you have now made it to the bottom. And that does have a significant impact on what happens next, because now the sled is no longer on an incline, but has whatever velocity you found here is now the initial velocity for it being on horizontal ground. Also, it's now experiencing 3 forces that are different than before. Weight, sure. Normal force, definitely, and those should be equal. But the normal force is now increased because it's no longer on a ramp. The normal force went up. There's no angle involved, which means the frictional force also increased. And friction is the only force acting in the x direction. And it's acting against the direction of motion. However, that's really immaterial. Net force equals ma. It's It's accelerating, it's slowing down. How do I know that? Because that tells me it stops. So I can kind of figure out that it must be slowing down. Net force in the y direction, O equals 0. So minus friction equals MA. And normal force equals mg. There, I've done everything I can with Newton's laws. That's what Newton's laws give me. But the coefficient hasn't changed. So I could still use the coefficient to figure out what the new acceleration is. Because friction is equal to mu times the normal force. Friction must also therefore be equal to mu mg. So taking all of those things and combining them together, I get minus mu mg, that was friction, equals ma. Cancel the m's, and my new acceleration is minus mu g. The minus sign isn't accidental. We have been treating down the ramp as positive. We should continue to treat to the right as positive. This also ensures that the acceleration works out to be a negative number because it is slowing the box down. We know that there's an initial velocity that was whatever we got from the final velocity for part A. So we have this number, whatever it is. And the final velocity is 0. We just want to know how far it slides before it comes to rest. Another motion equation. Arguably the same motion equation that you use in part A. So there it is. Use your numbers. That's number 8. Next. Excellent. That means there's time for the quiz. Was hoping for that. So since there are no other questions, you guys at home, no other questions? All righty. You have your blank sheet of paper out. I'm going to go ahead and stop recording because I don't need to.